Welcome everyone to the explanation of assignment 8. Usually I take alpha equals to 5, but this time let's take a different one, so we'll take alpha to be 7. Let's do the first question first. So we have to consider the function given by alpha plus 2 times y plus x cos y, so in this case 9y plus x cos y. We have to show that the curve that f with equation fxy equals to 0 has a tangent line around the origin, and we have to give an equation of this tangent line. So let's call the curve C, just for future reference. Okay, so the first thing that we want to check is that the point actually is on the curve. So let's compute f of the origin. Well, that's equal to 0 plus 0, so that's 0. So indeed, so the curve C is a level curve. Level curve of f. And now, of course, now that we have the level curve, we want to apply theorem 103, which will tell us that we have a normal, and therefore we will have a tangent line. But to apply this, we need to compute the gradient and to show that the gradient is non-zero. So let us compute the partial derivatives of f. So if I differentiate with respect to x, 9y is a constant, so I get the derivative of x cos y, which is cos y. If I differentiate with respect to y, then derivative of 9y is 9, and the derivative of the cos is minus the sine, so we get minus x sine y. Now let us compute the gradient of f in our point, which is the origin. That's equal to the cos of 0, which is 1, and that's 9 minus 0, so that's 9. So now we can apply theorem 103. Which tells that our level curve has a tangent line around the origin, because the gradient is non-zero. Okay, so that deals with the first part of the question, where we have to show that we have a tangent line. Of course, we also have to give the equation of the tangent line. For that, you can basically follow example 104 in the book. So what we can say is, furthermore, by remark 101, we know that the gradient is a tangent line, so therefore we have that the point is on the line precisely when the gradient in the point dot product and then the vector xy minus the origin equals 0. So this formula is easy to remember because it's very similar to if you have the normal of a plane. You just have 3 variables instead of 2. So if you have a normal of a line or a normal of a plane, you just the only difference is that you have 2 variables instead of 3, but otherwise the equation is exactly the same. Now we just work this out. So the gradient, we just computed that. That is, let me show you this gradient over here. We computed that over there. So that's equal to the vector 1, 9. And this vector is just x, y, because it's x minus 0 minus y minus 0. And then this dot product is just, so we get x plus 9y equals 0. So that is an equation of the line, and if you want, you can also write it in the form where y equals, so we get 9y is equal to minus x, so y is equal to minus x over 9. Both are perfectly fine equations of the line. Let us continue with the second question. So we consider the function f given by x squared minus y squared, and we have to explain why we cannot use the implicit function theorem to show that this equation, the equation fxy equals 0, defines y as a differentiable function of x near the origin. Well, if we wanted to apply the implicit function theorem, we need to check, if we want to write y as a differentiable function of x, we need to check the partial derivative of f with respect to y. Right, so we can compute this partial derivative, which is equal to minus 2y, and therefore the partial derivative in our point, which is the origin, is equal to 0, and therefore we cannot use the implicit function theorem. Right? So So we cannot, let's write it out, we cannot use the implicit function theorem because one of the requirements, namely that this is not 0, is false. Right? We computed it is 0, therefore we can never use the implicit function theorem. Okay, let us continue with the next part. Remember in the worksheet we did a similar question, but then we showed that even though we cannot use the implicit function theorem to show that y is a function of x, you can still prove that in that case y was actually a function of x. In this case, the goal of the exercise is to show that really y is not a function of x. So, first thing that is stated is that we should draw a picture of the solutions. Okay, so the function f is written over here, so x squared minus y squared equals 0. So if I equate this to 0, then we get that x squared minus y squared equals 0, which gives me x minus y times x plus y equals 0. Remember, this is similar to what we did in a very early assignment in the course. So then we get x equals y or x equals minus y. But actually in that case it was with inequality, so that was a little bit more complicated. In this case, well, we just have these two solutions. So if we draw this in the picture on the left hand side, we get these two solutions. Remember, what we have to show is that this equation does not define y as a function of x near the origin. You can already see that, because if I take a small circle around the origin, now I can already see that there are 2 points on the same vertical line, which means that, but if I have a function, I can only have a single value for every x value. So from the picture we already get the intuition that it's not possible for y to be a function of x in any small disk around the origin. And what the rest of the exercise does is we're going to formally prove this. Okay, so we're going to assume that we can actually write y as a function of x around the origin, which means there's an interval around the origin and there's a small disk, such that if my x is in the interval and the vector xy is in a small disk around the origin, the equation fxy equals 0 defines y as a function of x. So in this exercise we will show that y cannot be written as a function, and we're not even worried about differentiability. So we're actually showing that y cannot be written as a function of x. Now, since 0 is in the interval, and the interval is open, means that there exists a small delta prime. I use a different delta because I already have another delta. So there's a small delta prime such that there's a small interval which is in I. So that could be like, in my picture, could be like this. So that could be the delta prime. Then I want to take the minimum of those two deltas, which I will call delta double prime. So it's the minimum of delta, minimum of the radius of the black circle, and the minimum of, and the other delta is the size of the interval. It gives me, well, not 2 times, but half times the size of the interval. And this will again be a strictly positive number. And in this case, we see that delta double prime over 2 is in the interval. Okay, what do we have to do in B? We have to show that both of these two elements satisfy this norm inequality, right? So, for instance, for the first one, we have to show that the norm of delta double prime over 2, comma delta double prime over 2 minus the origin, we have to show that this is less than delta. So, in other words, this point is actually in my black circle. Well, let us compute this. Well, this origin does not change anything, so what I get is the square root of delta double prime over 2 squared plus delta double prime over 2 squared, which is equal to the square root of, well, you can check yourself, you get this over 2, which is equal to, remember delta double prime is positive, so it will be delta double prime over square root of 2. I have to show that it's less than delta, so let me just repeat the delta double prime over 2 over square root of 2. Well, what do we do now? Well, we know delta double prime is definitely less than delta because it's the minimum of delta and something else, right? So first let's remark that it's strictly less than delta double prime, because I divide by a number bigger than 1, namely square root of 2. And this thing is going to be less or equal than delta. Because, again, delta double prime is the minimum of delta and something else. So it's definitely less or equal than delta. So we have proven that this expression over here is strictly less than delta, which was what was required. Okay, I will not write out the second point, but the whole computation is exactly the same, because minus delta double prime over 2 squared is the same as delta double prime over 2 squared. So that's just the same. Right, so let's write this. Of course, you should write it out yourself, but check yourself. But in this explanation, I will not do this. And now finally we have to show that both of them satisfy the equation, but at most one of those two vectors can be on the curve where y equals g of x, which shows that, as it's explained in the original exercise, it shows that that the original assumption was false, that we cannot write y as a function of x. Okay, well, for the first part we need to show that f of delta double prime over 2, delta double prime over 2, we need to check that this is equal to 0. Well, that's equal to delta double prime over 2 squared minus delta double prime over 2 squared, which is indeed 0. Okay, similarly, let's write it out for the other point. This will be, we just get a minus over here, but since we're taking a square, this is still going to yield 0. So indeed the first part is clear. Both of these points satisfy fxy equals to 0. Now you can already see in the picture over here why it's not possible for both of them to be in the graph of a single function, because if one of them is in there, function can only take a single value. So now the question is, how should you write this down? Okay, we have to show that at most one of the two vectors satisfy the equation. So let's suppose that the first vector that satisfies the equation. So suppose the point x, y equals delta double prime over 2, delta double prime over 2 satisfies the equation y equals g of x. Then, now we need to show that the second one cannot possibly satisfy this equation. Well, let's look at the g of the point delta double prime over 2. This is now equal to delta double prime over 2, according to what we suppose, but that's not equal to minus delta double prime over 2. Right? These are different numbers, because delta double prime is strictly bigger than 0. So the other point does not satisfy. Does not satisfy y equals g of x. So what did I do over here? I showed that one of the points satisfies the equation, then I show that the other point does not satisfy the equation. So now let me continue over here. Now by exactly the same argument, I will not write it out because I'm out of space, but you can do that yourself. So you can also say, suppose x, y is equal to minus this one. The other point satisfies y equals g of x. Then, and so on, you will find that the other one does not satisfy, exactly because of the same reason. And therefore we have shown c, and therefore we have shown y is not a function of x, near the origin. Alright, let me continue with the final question, which is, we have to use theorem 78 to prove theorem 95. So I've already written theorem 95 over there. It tells me that the directional derivative in the direction u of f is equal to the gradient of f in the point dot product u. And theorem 78, you can look that up yourself, is just a chain rule. So, it's not clear how to approach this, but thankfully we have a nice hint. We should consider this function and its derivative at 0. Okay, well let's do that. See, if you don't know what to do, let's just follow the hint and see what we can get. So let's compute the derivative at 0. How should we compute this? Well, another major hint is that the question asks us to use theorem 78, which is the chain rule. So we should use the chain rule here. Well, how do we use the chain rule? Well, see, f is a function of two things. Let's call this one x and this one y. So we have f of x and y, and x is equal to a plus tu1, and y is equal to b plus tu2. So in other words, I have my function g, which is as f, which depends on the points x and y, and they both depend on t. Right? So if I want to draw a tree, it's like this. So then the chain rule tells me that I have to compute the derivative of f with respect to x in the point where t equals 0, so that's a plus 0, b plus 0, times the derivative of x with respect to t, let's write it as dx dt in the point 0, plus f sub y in the point a plus 0, b plus 0, times the derivative of y with respect to t at the point 0. Yeah, so let me write it like this so that it's clear to which variable we're taking the derivative with respect to t. Now I can just fill this in, so a plus 0 is just a, so this is fxab, and dx dt, let's do this in blue. So what is dx dt? Well, if I differentiate with respect to t, I just get u1. And let's also do it for y, dy dt is equal to u2. Right, so especially also in the point 0, I just get u1, and for the second one I get f sub y, ab times u2. Okay, so right now we've used theorem 78. How do we proceed? Remember, we're trying to prove this statement over here in the top right, over there. So we want to write it like something with the gradient dot product u, and I already see, oh, this is exactly equal to the gradient of f dot product u. Right, this is the natural thing to do because this is what we have to work towards. Okay, now the question is what next? Okay, well we have to show that this expression which you computed over here is equal to that. What we've shown so far is this is equal to the derivative of g at 0. So in other words, if we can prove that the derivative of g at 0 is equal to this directional derivative, we are done. Well, you can do this in two ways. You have to use the definition, so I will start with the derivative of g at 0. So you can also compute it in a different way. I can use the definition, which is that the limit for h to 0 of g of h minus g of 0 over h. Remember from first year, that is the definition of the derivative of a single variable function. And now I can just plug it in. So the g of h, well, what is g? G is f of a plus hu1. So this is f of a plus hu1 and b plus hu2. And the g of 0, that's equal to the f of ab. So let me point towards using this formula over here. This is just what I get if I get g of h and the g of 0. And we divide that by h. Aha, but now we have a very familiar expression because this is precisely the definition of the directional derivative in the direction u of f in the point ab. Right? So another way to approach this is to do it the other way around. So you can also start here and then write it out using the definition, and then realize that you can rewrite the f's in terms of g because of this expression. So there's actually two ways of doing this. In any way, it's clear from the first computation, which I did over here, and the fact that you have to prove this, that you have to equate those two things. So you have to start with one of them and use the definition to get to the other one. And this ends the last exercise and also ends my explanation of assignment 8.